Welcome to another JSO tutorial. Today we're going to talk about nonlinear least squares in Julia. So this tutorial will use some familiarity with jump and with the subject of nonlinear least squares. I have a few packages that I'm going to use. Maybe I won't use them all today, but this is essentially the packages that I need. So first, what we are talking about when we say linear least squares is the problem of minimizing, usually something like minimizing the norm of a vector function f. So here big F is gonna be something from the Rn to Rm. Of course I don't have big R, so okay. So when you study optimization, one of the first examples that we have is the Rosenbrock function. And the Rosenbrock function is a nonlinear least squares problem, except that is not a very useful problem in the sense of the linear least squares, because it only has two residual functions and only one solution, which has a zero residue. So it's not very interesting in that sense. The Rosenbrock function is something like f of x equals x, x1 minus 1 squared plus 100 x2 minus x1 squared. So if you look at this function, except for the half here, you're gonna have x1 minus 1 being one residual, and 10 times x2 minus x1 squared being another residual. So one can write this function as a nonlinear least squares like this. Here we ignore the half because it doesn't really matter, except when we're trying to write some equations. So in the solution to Rosenbrock, I'm gonna have a new residual. Okay. So in JSO, specifically inside NLPmodels.jl, we have a subtype of the abstract NLP model, which is the abstract NLS model. So using NLP models, my keyboard shouldn't be so loud, sorry about that. The abstract NLS model should be a subtype of the abstract NLP models. Sorry, that's just model. Okay, and if I have an abstract NLS models, I have some specific functions for dealing with the residual function. So first things first, let's create one simple residual, a simple nonlinear least squares by passing only the residual and using automatic differentiation. So forward diff. We're gonna define NLS as an AD NLS using that function. Since I don't want to make the example dependent on that f, I'm redefining it here. And I'm gonna choose the same starting point as the Rosenbrock function. So here I have the function f. Here I have f. Here I have a starting point. And I need to inform how many equations there are in this function. I could simply evaluate it, but since I'm trying to be efficient, I'm gonna pass the number of equations. Okay, I'm gonna close this here. So this defines a nonlinear least square, and the main functions that we want to use is NLS. So the main functions that we want to use is residual at some specific point and Jacobian of the residual. Okay. So there are other functions that may be of interest. For instance, the Jacobian product. You can use jprod residual times once, for instance, and the transpose of the Jacobian residual. This essentially follows the same notation in NLP model, except that it has an underlying residual in the front. The difference starts to appear when we look into the Hessian. The Hessian of the residual. And the Hessian of the residual is going to have an argument here that is not related to the constraints. So this is only looking at the function f, and the Hessian of the residual is the combination of the residuals of f, this function. So this has residual is going to be something like, so the Hessian times vi. So if we want the Hessian times 2, I'm gonna have this here. So notice that when we look at the problem in this form, you can look at the function, the gradient, and the Hessian of this function. And if you look at the objective here, and you look at residual, the norm of the residual square divided by 2. I forgot to use norm. So here is the same thing. If I have the gradient and I use explicitly jack residual times residual, I should have the same thing. And the same is true for the Hessian, except that not every model is going to implement the Hessian function because it involves the... So not every model is going to implement the Hessian of f, small f here, because it involves the product of J transpose J. So it's very inefficient for very large problems. So some problems are some models are specialized and they don't provide this. Okay, so be aware of that. If you compute the Hessian of x here, and you use the Hessian of the residual at the residual, which is this part, plus the Jacobian of the residual times the Jacobian of the residual, is going to be the same thing, except that this one is going to be symmetric. So be aware of that. You're going to want to use only the lower half. Okay. So this is the basic API. So right, basic API. You're gonna have residual, jack residual, and has residual. This is the main ones. If you want to use the product, you have Jacobian products and J transpose product. And you also have H-prod residual as well. Okay. The default way of defining nonlinear least squares is, I mean the one already provided by NLP models is using AD and LS model, but usually you're going to want to write something simpler. So this is where jump and NLS models jump NLP models jump come along, which I forgot to install. There you go. So in jump, let's write down the same Rosenbrock function. So we're gonna have a model with two variables, x1, x2. You have a set start. Yeah, there you go. Minus 1.2 and 1.0. And if we're gonna write the problem as Rosenbrock directly, you will use this. The objective, which is nonlinear, should be minimizing x1 minus 1 squared plus 100 times x2 minus x1 squared squared. Okay? Except that by writing it this way, you have no information about f directly. You're gonna have something like this. For a simple Rosenbrock problem, J transpose J is not an issue. But if you're gonna work with large-scale nonlinear least squares, you're gonna want a specialized solver, one that does not produce J transpose J directly. So one way to handle this is to use our NLS models jump, which is still uses jump. Essentially, it's kind of an back end to jump. It converts the jump problem to our NLS model. Instead of writing an objective, you're gonna write nonlinear expressions for each of your residual functions. Okay? Oh, I forgot 10 times here. And then what you're gonna do is write math opt NLS model, and you're gonna pass these models as well. You can give a name to it, Rosenbrock NLS. So that's gonna be x0i. Okay. So my memory on jump is not the best. So you have an NLS model. There's no pretty printing for it, sorry. And if you ask for the residual at starting point, you're gonna have the same thing. The residual at the solution should be 0. And if you ask for the Jacobian, it should be sparse, because jump handles the sparsity. So jump is a great modeling tool, and essentially what we are doing is using that power to provide our model with great information. So instead of writing the objective function directly, you write an NL expression. Notice that you have the other information as well. So if you want the Hessian, the gradient, you have all that. But you also have the option of using specific methods, okay? For instance, some Gauss-Newton method. Let's write a more interesting problem and solve that problem. So what we're gonna do is write something for a model with residual being, I'm gonna use the logistic. You're gonna have something like beta 1 over 1 plus exponential of minus beta 0 minus beta 1 xi approximately yi. So let me write as frac. Okay, so let's write something like this. First, let's create some fake data. I'm gonna use x between -1 and 3. Let's use 30 points. And I'm gonna say that y is have to use dot divide dot plus exponential dot, and what I want is something. I'm gonna have to modify this so I can find a good value. X, so dot here, and I'm gonna add a random factor inside exponential. So rand n times 0, 1. And let's look at this. Okay, so I should also write gr. So that's better. So I'm gonna fit this data, and I'm gonna use a model that is something like 1 plus exponential of beta 1 minus beta 1 minus beta 2 times x, okay? If I plot my age of, let's say, for 1.5 in the interval extrema x line way 2 color red, I'm gonna have something terrible because it's not 4, it's minus 4. Okay, so we can see that the model is working as expected. It's not in the solution, so that's fine. And now we're gonna write the nonlinear least squares problems related to fitting this data. Okay, so using jump again, I don't have to use jump again. I have a model, I have a variable beta 1, 2. I'm not gonna pass any starting value, and I'm gonna create a bunch of equations, bunch of residual functions essentially, which are gonna be this, and here I'm not using that how to say, the register function, because I don't remember how I should write it, and it has some problem with vector value input, so we're gonna avoid it. So fi is gonna be this model minus this expected value, and our NLS model is math opt NLS model f, and the name of this is logistic. Invalid redefinition, of course, that's why I didn't want to use f. Let's write res. So the starting point of this model should be zeros. That's the default for jump, and the residual should be large. I guess this is large, and we should have a smaller residual when we're closer to the solution, which is minus 4 and 1.5. Okay, so the residual is smaller, at least visually. Now let's solve this. So I'm gonna use JSO solvers, which has some solvers for this kind of problem as well. And the solver that I'm gonna use is trunk. Should be trunk with a K, but I haven't loaded JSO yet. So trunk was first implemented for general nonlinear unconstrained nonlinear optimization, but we have made a different version which instead of using Newton, it uses Gauss-Newton in the internal subproblem. So it's essentially a Gauss-Newton with truss region. It uses Krylov.jl internally, and this is the first time it's just for the precompiling, okay? It's not because it's slow. So the function value, which is the residual, goes to 3.7 to the times 10 to the minus 2. The dual feasibility is very small, and it says that it's a first order stationary. Let's print the output and see that this solution is minus 3.6 and 1.5, and compared to this value here, okay, it's close to the original. Due to the error, it's expected. So beta is gonna be output.solution, and this is the solution. Yeah, there it is. So it looks great. Okay, wonderful. So one thing that happened when I was fitting the COVID data was that I was trying to use something like this, but I wasn't doing from 0 to 1 as a percentage of the population. I was doing with a random value. Not random, but with an additional value. Let me just copy this, suffer more. And the other thing that I'm gonna do, so essentially this one here is gonna be a random value, and I'm gonna say from 1000 to 4000. It's one random value, okay? And the other thing is that I'm not gonna use rand anymore. It's gonna be rand n. Oh no, I don't need to use random value here. Although it's not great, let's use this, which is a better example. So I'm still looking at the same kind of problem, but now I have 3 variables, and this third one is beta 3. When I was trying to solve this problem, I had an issue, and I ended up having to use bounds because it was converging to a different solution. So I'm still using trunk here. Now I actually don't want to see the whole solution, so I'm gonna use logger. With logger, no logger. So it doesn't print everything. And it has found, yeah, it has found the solution easily, okay? But what was happening for me is that it was converging to a different solution, which was using the mean value of everything. And these guys were positive but 0, and it shouldn't be positive. So I was adding a constraint that beta 1 should be positive. So that's what I'm gonna do here. I'm gonna set a lower bound, and apparently I have to do it this way. Yep. So if I look at NLS meta LVAR, I have a bound here for 0, and if I ask if NLS has bounds, it's gonna be true. So what I had to do was use strong to consider those bounds. Here I'm doing the opposite because it should be an upper bound, but just to see that it is using those bounds, I'm using LVAR greater than 0. Let me just copy this. So here you can see the objective value is terrible. It tried to go to negative beta 1, which is the solution, and this doesn't even make sense. So this was happening because it was converging to a different solution. So I had to use bound for beta. Okay. So here I'm gonna use uvar. So now it's failing because my model has changed. Age of beta x is now beta 3 divided by 1 plus exponential of minus beta 1 minus beta 2 times x. Okay. This Tron solver solves nonlinear least squares problems with bounds, so should also consider using that. Okay. So this is the basics of nonlinear least squares. The one more advanced option that sometimes appears is having nonlinear least squares with constraints. So if you know the NLP Models API, you know that we have cons and jack for the constraints. And to define a problem with constraints, you can simply add the constraints directly here. For instance, let's say the beta 2 this is not gonna make any sense, but beta 1 square plus beta 2 square equals 1. Okay, so the constraint value at the starting point is 0, 0, minus 1. So an option is to use Canolis, which is a solver that we have created and it was submitted already, hopefully in the last round of revisions. And you can use Canolis to solve. Oh yeah, this doesn't handle bounds, unfortunately, yet. Okay, let's just get the output. So there it is. The solution satisfies the constraints up to 10 to the minus 9. And the dual feasibility means that he found a solution as well. So of course the solution is terrible because I added an artificial constraint to the problem. I'm gonna use data frames and CSV. Actually, I don't need data frames, just CSV. And I'm gonna write data equals csv.read turbo.csv. Y is data x, x is data x, y is data y. Y is data y. Scatter xy leg equals false. And we wait. Here I'm gonna copy this. And our model is cubic over cubic. What is this? Here we go. And it has 7 parameters, and they are beta 1 plus beta 2 times xi plus beta 3 times xi squared plus beta 4 times xi cubed divided by 1 plus beta 5 times xi, beta 6 times xi squared, beta 7 times xi cubed minus yi. There's no constraints, or there are no constraints. This is gonna be called turbo. Yep. And output is with logger, no logger, do trunk NLS. I forgot to set the starting point, which is very important for turbo. 1,440, 1,440, 0703, 003. Start equals beta 0. I have to say beta 0i. So the difference is amazing. So now I'm gonna plot. I have to say that beta is the solution, and I'm gonna plot at the extreme of I, line way 2, and color red. And I forgot to say exclamation mark. So there it is. Turbo, I'm not sure if the solution is great. So the dual feasibility is actually very large, but the starting residual was also very large, so the relative tolerance came into play here. So we saw today how to solve nonlinear least squares problems and how to access the residual function and its derivatives using NLP models. So with this you can implement your own solvers, or you can use Jump to write your problem and solve it with one of our solvers or some other solver. You can also use IPOP to solve these problems. So if your problem is small enough and you prefer to use a well-known solver, you can try that. But if you want something more specialized, we have a few options. Okay, so this is it for today. I hope you guys enjoyed it, and I'll see you guys next week with more JSOL tutorials. Thanks for watching, and please subscribe.